Thank you, Arnob and Pinaki, for organizing this very interesting conference. It's broad, but not so broad that you can't understand half the talks. So I learned a lot, and so this talk will be very different from the other talks in the sense that there will be no simulations, no plots. Well, there might be one experimental plot from an experimental collaborator, but that's it. And okay. So basically what I want to convince you of is there are many kinds of active solids are actually like externally driven solids, and what I mean by like is that their long-time, large-scale hydrodynamic correlators of these two systems are the same. Hydrodynamics can only give you information about asymptotically small wave number and small frequency correlators. That's all hydrodynamics can give you, okay? And I want to convince you that these two can be similar, okay? So we all now kind of know what active matter is. These are particles, each of which have an independent access to some energy and uses that to do something, okay? Typically, we think of these systems as, sort of particles that have some internal batteries inside them, or, particles that can take up energy from an exothermic reaction that's being carried out in their environment, and you keep this exothermic reaction off chemical equilibrium by continuously supplying continuously supplying reactants and removing the products, right? But these are not the only kinds of active systems. So in fact, if you have any system in which you have a flux and you look at a plane that is transverse to the direction of the flux, the dynamics in that plane is active. And you can see that it has to be active by this definition because every particle in that plane has an independent access to a free energy, energy because of the flux going through that surface, threading through that surface. And this is sort of my contribution to increasing the number of reviews in active matter. And there, so one very simple example of this kind of active system is when you have two bulk systems, when you have an interface between two bulk systems maintained at two different temperatures or two different chemical potentials. The 2D physics of particles or objects in that interface is active, okay? So then what is the fundamental difference between sort of a standard driven system like, a current carrying wire or a sheared fluid? So the difference is one of symmetry. So if you have an externally driven system, the drive itself breaks the symmetry of the system, whereas activity doesn't break a symmetry of the system. So here in the bottom, the systems are in green, right? So activity is not breaking any spatial symmetry in this plane. Okay, that is a fundamental difference. And but if it has, and that matters a lot, of course. So you can talk about isotropic active matter, spatially isotropic active matter, but how can I talk about spatially isotropic driven system if I'm explicitly breaking a rotation symmetry there? I can talk about spontaneous breaking of rotation symmetry in active matter. How can I talk about spontaneous breaking of rotation symmetry in this kind of a system? Because I have already broken rotation symmetry. There isn't any rotation symmetry. So why am I asking this question at all? I mean, this question now seems kind of stupid, and the answer seems to be obviously no. So of course, driven solids and active solids should be different. So why am I asking this question at all? Well, the reason for this is something you kind of learn in high school. So, in high school, you sort of know about point groups of crystals. That means crystals break both translation symmetry and rotation symmetry. But you also know that crystals have sound waves, right? So sound waves or phonons are Goldstone modes corresponding to broken translation symmetry. And those are the only soft modes in your system, because if you had something else, you'd have to learn about them in school, because, if you had other soft modes, they would couple with your phonons, and you'd have to learn about them in school. So what happened to the Goldstone mode of broken rotation symmetries? Where did they go? Yes? You had a question? So where did the Goldstone modes of broken rotation symmetry vanish? Well, they didn't vanish. What happened is they had become massive, and they became massive because of basically the Anderson-Higgs mechanism. The non-fancy way of saying it is that if you try to rotate a bit of the solid, you also stretch bonds. So think of a sort of a network of springs, okay? And now try to rotate a bit of that. So you always stretch bonds. But if you can take that spring network and you can push a bit of that network ahead without rotating anything. So rotation is always coupled to translation in a translation symmetry broken system. And it's easiest to do this, to see this actually not in a solid, but in this thing called a smectic. So a smectic is a one-dimensional periodic structure in a d-dimensional system. So it's a periodic array of d-1 dimensional fluid layers, okay? And so where is the rotation symmetry breaking here? The rotation symmetry breaking is that you don't know what is the one direction that is being picked out. You could pick out any direction in space. You have the layers in one particular direction, and that's your rotation symmetry breaking, okay? And many smectics, but not all, are composed of sort of a periodic array of these kind of nematogen, so elongated molecules, which have sort of no correlations in space in d-1 dimension, but stack on top of each other. Okay, but this is so if they didn't stack on top of each other, this would have been a nematic. They would have some orientational order in space, but no translational order. And then you had a soft mode for those nematics, which is the director. Okay. So what this Anderson mechanism tells you, which is a fancy way of saying what I just said earlier, is that if you try to tilt these director fields, that corresponds, because of the coupling between the layers and the director, that corresponds to a tilt of the layers themselves. So delta n perp, which is the, which would have been the soft mode of a director in a nematic, is basically now proportional to del perp u, okay, where del perp u is the tilt of the layers, local tilt of the layers. But you know that in equilibrium, a free energy cannot contain delta n perp squared because of rotation symmetry. And because of this, because I told you that delta n perp is proportional to del perp u, now you know that in a smectic, a free energy cannot contain del perp u squared, which means a smectic cannot have a tension. So for the younger people in the audience, what would a similar argument in a solid tell you? Any takers? It tells you something about the free energy of a solid. What does it tell you? So what it tells you for a free energy of a solid is that the free energy of a solid can only depend on the strain tensor, on the symmetrized part of the displacement gradient tensor. Because you know that the curl of u in a solid is a rotation. Your free energy cannot depend on rotation. Okay? So yeah, so the upshot of all of this is that there is no massless orientation mode that's possible in any translation symmetry broken system. Okay. So, okay, how does, and by the way, I should, so this is basically the thing that will allow me to show that in many driven and active translation symmetry broken states, the hydrodynamics are equivalent. And this is a sort of a disclaimer. Only the spin wave dynamics, which means that I'm ignoring all defects, are similar. The defect dynamics is different, and I know it's different. Okay, and this is a really nerdy point about a particular system in which a particular case in which I know that defect dynamics is different. Okay. Okay. So let's first take the smectic and see why the driven and an active smectic should be similar. So this is actually a polar smectic. So delta n perp is del perp u. There is a force along the direction that these guys are pointing in. So the force is Fz, which is proportional to del perp n perp, which is del perp u squared. And if you have a driven smectic, the argument that I used for rotation invariance doesn't work anyway. So you again have you have no invariance under tilt. So you get a force density which is proportional to del perp squared u. So this is, in both of these cases, you see that you have a tension that has emerged. Okay, so in both an active smectic and in a driven smectic, there is a tension. Okay, in an equilibrium smectic, there is no tension, and the smectic is polar, so there is no n going to minus n symmetry. So it's moving in the direction it's pointing in. Okay. Okay, so let's write down the hydrodynamics of this object. So first, let's look at the hydrodynamics of driven smectics. This appears, and this was, looked at years ago in the context of charge density waves in superconductors, etc. So this is an anisotropic KPZ, and I'll come back to this. And if you have a polar smectic, and basically I have gone into the co-moving frame here. If you have a polar smectic, you have a very similar equation, except that I have not. So here, even here, there was a term which was like lambda 0 del ZU in the driven case, but I absorbed that into a redefinition of the direction of motion of a coordinate. And here, the only distinction between an active and the driven smectic is a relation between lambda 0 and lambda perp. Okay. But this is actually immaterial for hydrodynamics of the system. And that's because, as I have done here, I can also reabsorb lambda 0 in a redefinition of z, where z is the direction of motion. Okay? So I can redefine z and completely eliminate lambda 0. And then you can see that this equation and this equation are exactly the same. And people have looked at the properties of this actually from a long time ago, actually. This used the flow diagram was from 1990s. And what you know is that if lambda perp and lambda z have opposite signs, the nonlinearities become irrelevant. If they have the same sign, it basically becomes a KPZ and you don't have a fixed point. That's what you know. Okay. Well, but okay. Why were they equivalent? They were equivalent because I could remove lambda 0 altogether by a redefinition of z, right? If I have a quench disorder in the system, if this xi here is not an annealed noise but a quench noise, then I cannot do that rescaling. This rescaling, I don't want to set up a TV. This rescaling depends on there being a convenient delta function in the correlation of this noise. So if I cannot do that rescaling, what happens? Then is an active and a driven smectic distinct in the presence of quench disorder? Well, let's see. So now I'll go specialize to 2 dimensions. Just for simplicity, there is no particular reason. I can do it in arbitrary dimensions. So now now lambda x, which was lambda perp earlier, because it was in d minus 1 dimension, has to be fixed to lambda 0 over 2 due to rotation invariance. But notice the structure of this equation. So there is a lambda 0 del ZU, and because of the presence, so I want to first look at the static structure factor of this, the equal time correlator, so the static properties. And because you have a lambda 0 del ZU, you can immediately throw away the lambda z del ZU squared and kz del Z squared U, because they have higher orders in gradients. And I'll show you post facto that everything still remains consistent. Okay. So if I throw those 2 away, then what I get is this equation. This is the 1 plus 1 dkpz, whose exponents I know. And more importantly, the lambda x over lambda 0, which is the coefficient of this guy, is not renormalized. So though the lambda x over lambda 0 is fixed by rotation invariance here and is not fixed by rotation invariance in a driven system, in neither case is it renormalized. So because it's not renormalized, the fact that it has a particular value does not change the scaling at all. In both cases, I have the same exponents as the kpz, 1 plus 1 dimensional kpz. That is, the dynamical exponent becomes the anisotropy exponent here, and the roughness exponent is the roughness exponent. Okay? Yeah. So the constraint of rotation invariance doesn't matter. And then you can basically use these exponents to check that the thing I did, which was dropping del z squared u and del z u whole squared, is okay, and it all works out fine. Okay, good. So that's for the smectic. So I have shown you that a driven smectic and a polar active smectic are equivalent both in the presence of annealed noise and in the presence of quenched noise. Okay. Now let's go to a solid. Okay. So you can have a polar solid in which you have a bunch of a crystalline state in which every particle is a polar particle and it's moving in the direction it's pointing in. And you can have a sort of an externally driven two-dimensional crystal. Okay. And the dynamics of the externally driven two-dimensional or three-dimensional crystal was discussed years ago by Lahiri and Ramaswamy. And this is relevant in multiple contexts. It's relevant for crystals that are sedimenting under gravity. It's relevant for vortex lattice arrays in superconductors that are moving because of driven vortex lattice arrays, etc. Okay, and these equations are actually quite interesting in themselves. So you can immediately work out the eigenfrequencies of this, and you'll notice that if alpha 2 and beta 2 here are greater than 0, you get a sound mode without inertia. This is a non-reciprocal system. This was years before the word non-reciprocal was used in this context, but this is a non-reciprocal system. If you have, if your alpha 2 and beta 2, this product is less than 0, you have an instability. And the point between where you go from the stable solid with sound modes to an instability is an exceptional point. And the physics of that exceptional point is actually quite exceptional. It's basically, this is Dibyendu Das and Mustansir Barma looked at this years ago, and Satya Majumdar during his PhD looked at this again years ago. Okay, it has something called fluctuation dominated phase ordering, etc. I'm not going to go into that. Today I'll always remain in the regime where the solid is stable. Okay. So then, sort of 20 years after this, we wrote down the hydrodynamics of active solids, and it looks very similar to the driven solids, except that now beta 1 and beta 2 are related. Okay. But again, this doesn't matter for the hydrodynamics. And you can see that by noticing that I can again completely eliminate beta 1 in both cases by redefinition of Z. And that changes alpha 1 as well, but alpha 1 is arbitrary. Alpha 1 is not fixed by rotation invariance. So the hydrodynamics of both of these systems remains the same. Okay, but again, what happens with quench disorder? I can't do that rescaling if I have quench disorder. Well, again, let me go to 2 dimensions, because 2 dimensions is the case that's interesting. And so you have this set of equations, and you can immediately calculate the static structure factor. And you notice something. You notice that you need alpha 2, beta to be greater than 0. You need this condition for stability. And then you notice that as long as alpha 1 and beta 1 is negative, this coefficient, this denominator, cannot vanish for any value. Right? If this denominator cannot vanish, then you see that for all directions of wave vector space, uz squared and ux squared average scale as 1 over q squared, where q is, so I should have mentioned that q is the wave number, okay? And then you can show that if it vanishes as 1 over q squared, there is no relevant nonlinearity in the problem. You cannot cook up a relevant nonlinearity here, okay? And again, the relation between beta 1 and beta 2 doesn't matter in any of this, okay? You have a more interesting case when alpha 1 and beta 1 is greater than 0, and then this object, the denominator, vanishes for some value of qx and qz, right? So there is some direction of wave vector space in which the denominator vanishes at this order. So you need a next order guy in the denominator, okay? And it vanishes precisely because that is the direction in which the sound speed vanishes. So what is the sound speed doing first physically? If you have a system with a quench disorder, but you're moving with respect to the quench disorder, then the quench disorder from your perspective looks like an annealed disorder. There's no difference between a quench disorder and an annealed disorder, right? If you're running past an arrow that's pointing in some direction, you've forgotten about the arrow after some time. Okay. But a fluctuation moves with the sound speed. If the sound speed vanishes for certain fluctuations, that means for those fluctuations, a quench disorder is like a quench disorder. And therefore, in those specific directions, uz squared and ux squared scale as 1 over q to the power 4, not as 1 over q squared. And then there are relevant nonlinearities for gradients in that direction. And I don't know much beyond that here. I couldn't do the RG. I tried to map it to the Ettas and Kardar equations, but I've not managed to do it till now. But importantly, there's still no distinction between an active system and a driven system, even in this case, okay? Okay, good. So I'm not sure whether I'll talk about this. Okay, let me quickly talk about this. So you remember, the idea that, active systems and driven systems are the same came in because the rotational Goldstone mode was massive. So if I don't make it massive, which is illegal, but let me indulge me for a second, if it is not massive, then they should not be the same. And indeed that's the case. And I never have done this usually, but what happened was Benoit Ledoux had this experiment on cell layers. And puzzlingly, what happened, what it looked like was that the cell layer was very solid. There was no neighbor exchange for days actually. This experiment goes on for like 2 days. But when they measured the velocity correlators or the polarization correlators, they found that the polarization correlators are not massive. Okay, I mean they have a decay, right? Which means that those correlators scale as 1 over q to the power q to some power. Okay. The orientational correlation. Okay, sorry. So let me actually say something more. So if theta was massive, then 1 over q to the power 0, then it scales like, it goes to a constant. Over q to the power alpha. Okay? Yes?
Orientation or the cell polarization or all of the above?
Sorry?
Sorry, I'm not sure. Can you distinguish between the cell velocity, the cell possibly orientation or polarization, and the motility direction? Which one do you mean?
So they measured cell velocity and the polarization, which was the apical basal sort of shift. So if you look at every cell, there's a sort of shift between the top and the bottom. They associated a pole vector with that. They measured that as a polarization, and they measured cell velocity. Both of them have a decay of this sort. Okay. So, okay, this was puzzling because I have expected theta squared to look like this. Yeah, I don't need the. And of course, this cannot be true at arbitrarily large scales and long times, because at arbitrarily large scales and long times, it should go back to what I was talking about earlier. But it can be possible at intermediate length and time scales, because you have a theta dynamics of this sort, and when this time scale, for time scales smaller than this, or length scale smaller than this, the theta dynamics essentially remains massless. What that means is I've actually illegally switched off effectively a coupling that is required by symmetry in my free energy, okay? And that coupling is relevant. So if that coupling was switched on, I'll move away from this fixed point, okay? So, okay, then after doing that, I can write down the theory again. I can do a nematic and a polar version. Let me not go through it. Actually, let me. So what's the theory? The theory is that you have a velocity that's proportional to some polarization. So you're moving in the direction you're pointing in, and you have a polarization that does its own thing, essentially, okay? In the polar case, you have this, because you actually eliminated this. So this is the lowest order ingredient possibility, okay? And if you do that and write these equations down in a polarized state, what you get is ux dot going as theta, where theta is the angle, and theta dot basically going as del squared ux. What you can immediately see from here is that the ux and theta beat against each other to give you a wave. Okay, it gives you a sound wave. And the thing in nematics is similar but not the same. I'm not going to talk about it. Okay, so it gives you a sound wave. Then you can basically immediately calculate that the displacement fluctuations are huge, enormous. Okay, which means that basically, if this were true at large enough scales, the tissue would be destroyed. Okay, there could not be a solid. So, and the important point for my sort of what I'm trying to establish is that if I had this solid in an external field, there would not be any 1 over Q4 divergence. The theta field would relax fast to the driving direction. Okay, so this divergence is a signature that the free spin solid is not like an externally driven solid, and the precise reason being that it has a free spin. Okay, good. So, and now I'll go on to three-dimensional solids, and before that I need to give you a little bit of background on what is called a liquid crystalline elastomers. Liquid crystalline elastomers are basically isotropic solids in which there are elongated objects which can spontaneously order. So that ordering breaks the symmetry of liquid crystalline elastomers. So in the reference state, these are isotropic. In the target space, they're anisotropic. Okay, and you can see that basically it can align in any direction you want. So if I had if it could align in this direction, I could rotate it, and it could align in a different direction. And those two states are configurationally different, but energetically the same. So you can go from this state to this state in a liquid crystalline elastomer without costing any energy. Okay, what that means is I can shear the nematic elastomer, and the cost of the shear can be made to vanish by the director field reorienting. Okay. So these liquid crystalline elastomers are sort of funny objects. There is no cost for a WZ perp shear, and these are sort of a weird cross between a sort of a smectic system and a columnar system. A columnar is a crystalline array of liquid columns. So if you look at the Z direction, the displacement field along the ordering direction, that looks like a smectic. The displacement field transverse to the ordering direction look like a columnar. Okay, and an active liquid crystalline elastomer has an additional stress which basically end up looking like a active cross between an active columnar and an active smectic. The point is, again, whether I have an external field or I have an activity, it doesn't matter for this. Let me go over this quickly. Let me not bother about this. Okay, so now what I'm going to talk about, oh, sorry, I needed to say one thing. Yes, 5 minutes, okay. Liquid crystalline elastomers have a higher symmetry than usual. It has an OD cross OD symmetry. So usually if you have a solid, it has a symmetry under rotation in space. This has a symmetry under independent rotations in target space and reference space. So it has a higher symmetry, okay? So that will matter. That's why I wanted to point that out. So now let me consider a liquid crystalline elastomer moving in a three-dimensional system, three-dimensional external medium, okay? So it's a frictional medium, a liquid crystalline elastomer is trying to move through that, okay? So I can write down the hydrodynamic equations for this case. I can write down basically to first order in gradients. I can write down a velocity, I can construct a velocity. Turns out that this chiral term here actually does not contribute in the elastomeric state. So I get back the equations of the driven solid I flashed at the beginning of my talk, okay? And this is really a consequence of O3 cross O3 symmetry of elastomers. What that means is this set of equations can be stable, because I showed you that this is stable in the earlier part of my talk. However, now let's consider a chiral elastomer moving in an external, active chiral elastomer moving in an external anisotropic medium, or a chiral elastomer driven by a field of some sort, okay? So I can consider a polar field or a nematic field, or I can consider polar anisotropy. All of these cases actually look very similar. I can construct this, and then let's not bother with the algebra. Importantly, what I get is that the eigenfrequencies have this structure, which means that this object is generically unstable. So here is a huge difference between a nematic in a chiral elastomer, chiral active elastomer, and then a chiral elastomer in an external medium, external field. A chiral elastomer in an external field is always unstable, it cannot exist, whereas a chiral active elastomer can exist. It also means that if you have a sort of a chiral tissue or a chiral cell layer moving through an external medium, that object, a three-dimensional chiral tissue moving through an external medium, that object is always unstable. It always has a specific size, it will break up after that, okay? And you could have a nematic anisotropy and it would still be unstable. Importantly, you could have any anisotropy and it would still be unstable. So basically, if you have an external reference, rotating with respect to that reference is not a symmetry, right? So you can have a force density proportional to curl of u, which is a rotation with respect to a medium. But if you have that, you can immediately see that, you have an eigenfrequency. I mean, this you immediately can solve, and you can see that you have an eigenfrequency that is unstable for, you have a pair of eigenfrequencies, one of which is unstable, okay? So what that means is that, as I was saying, three-dimensional chiral active solids don't exist in an anisotropic medium, or three-dimensional chiral solids that are externally driven don't exist, whereas three-dimensional externally driven, three-dimensional active elastomers can exist. So that is a distinction, and that distinction is a consequence of O3 cross O3 symmetry of elastomers. So it's a consequence of an extra symmetry beyond the sort of usual symmetries of a solid. Yeah, I'm done actually. So in fact, actually, if you had a real solid, so first of all, experimentally, elastomers are actually almost never available. Disorder makes the O3 cross O3 symmetry go to an O3 symmetry. And if you have that O3 symmetry, I can show that that is also unstable. So an O3 solid, a polar solid, is exactly like an externally driven solid. Polar active solids is like an externally driven solid. An elastomer is slightly different. So that's the only case I know where it's different, okay? Okay, so to summarize, what I've told you is that achiral solids are like externally driven solids in the presence of both anneal and quench noise. Chiral elastomers are different but only because of the O3 cross O3 invariance. And spectacularly, chiral elastomers in an anisotropic medium, chiral active elastomers in an anisotropic medium are generically unstable. Okay, so and this instability is not a consequence of what is called odd elasticity, but odd mobility. So yeah, okay, and these were the people with whom much of this was done. And thank you. Yeah. Bye.
Great. Questions?
In the slide where you showed experiments on motile cell layer,
Yeah.
you mentioned that they are very rare neighbor exchange. So,
Yep.
so is it like a solid flock?
Yeah, it is a solid flock. That's the whole point. It's a solid flock, but I told you just to start with that, in a solid, the director fluctuations are always massive, which means they're always of that form. Theta squared goes to some constant at small q. Here, they measured theta squared, and they found that it doesn't go to a constant, it diverges at small q. Okay, small wave numbers. That was the puzzle.
So is there any transition from the disorder to the solid flock, or?
How do you do the transition? I mean,
Like,
there can be it is
plot a-
confluent. It's a confluent cell there. You cannot create, I don't know how to experimentally go across that transition except by increasing the density.
Plot a order parameter and see that the system indeed goes from some disorderness then to the solid flock.
So as that, okay, so in time, as the density increases, it indeed goes from a disordered to an ordered state, but that's just because it's getting more and more confluent.
Okay, thanks.
Yeah.
Yeah, to follow up on that, so sorry, I have a hard time thinking in hydrodynamics. So what exactly does it mean they're not massive? They're not massive. So say I get some data from experimental simulation, it's flocking, it's solid, it's not rearranging, and I can think of at least 3 different microscopic interactions which are going to give me this.
Yeah.
So what is this telling me about what's happening locally?
It's not telling you anything about what's happening locally at all.
But
So
there should be a map between, say, coarse graining, my local interactions should give you hydro equations eventually, right?
yes, so the point is the hydrodynamic equations will always, okay, if you really coarse grain a microscopic model to really large scales, you will get the dynamics of a solid that I showed you previously. Okay, so in that dynamics of solid, there is not going to be a soft mode for display for orientational fluctuations. The point is you have a coefficient in that, so when you do the coarse graining, you will basically get an equation for the angle field of this form. Okay, and the point is this angle field, this is supposed to be good, but it's, okay. See, this is a time scale, inverse time scale, right? If you are below this inverse time scale, this term doesn't matter compared to whatever else there is in the equation, right? So if this term doesn't matter, the other terms, so basically you can be in a regime in which this other terms dominate over this term. At the small time regime, this term will always dominate, but you can be in a time window in which other terms dominate over this. That's all I'm saying. The microscopic theory, microscopic mechanisms will give you this in some form. The values of C, the values of gamma, etc., will depend on microscopic parameters. But that's the only thing that will depend on microscopic parameter. The form will not.